We are now looking at Poisson equation, which is an elliptic equation. It contains second-order partial derivatives of a field variable u with respect to x and y. It's a two-dimensional version of Poisson equation. And on the right-hand side is a driving function f. And the field variable is required to satisfy this PDE at all points in a two-dimensional domain, which is marked by capital omega. And the boundary of this domain is marked by del omega. There's a special case of this Poisson equation. It's called the Laplace equation, where the driving function on the right-hand side is 0. So this is the homogeneous version of the Laplace's equation, Poisson equation. What we have here is a boundary value problem, which describes in general the behavior of electric gravitational fluid potentials. For example, steady-state flow of groundwater in a homogeneous isotropic medium is described by the Laplace equation, the equation in the second blue box. Depending on the type of boundary conditions we prescribed, we use different naming conventions that get attached with the Poisson equation. For example, we have the Dirichlet problem, in which the governing equation in the previous page is valid, but on top of that, we are required to find the field variable on some domain omega, such that on the boundary del omega, the field variable u is equal to some given or prescribed function. The second version of this is the so-called Neumann or Robin problem, where we are required to find the solution that satisfies the governing equation that was shown in the previous page, but then its first-order derivatives are required to satisfy some given prescribed function on the boundary of the domain. So if the field variable has prescribed values entirely on the boundary of the domain, it's called a Dirichlet problem. If the first derivatives with respect to x and y are prescribed around the boundary of our domain, it's called a Neumann problem. Of course, in a given problem, at some points on the boundary, either u could be prescribed and at some other portion of the boundary, the partial derivatives, the first derivatives might be prescribed, and that would be a mixed boundary value problem. One physical interpretation of this problem, the Poisson or Laplace problem, is as follows. For example, you can fix the temperature on the boundary of a heat-conducting domain, and then if you wait until the temperature in the interior doesn't change anymore because it's being diffused, and then you reach a steady state, well, that temperature distribution, for example, at that steady state limit is what is described by the Poisson equation. Poisson equation, for example, as we saw in the previous page, does not depend on time. It doesn't have any time variations in there. It actually describes the field variables such as temperature or fluid pressure in a porous media at the steady state. So here's our Poisson equation again. Let's just try to solve it using a numerical method for example, the Dirichlet boundary condition. So the first blue box is our governing equation. The second blue box defines our boundary condition. And on the points x, y belonging to the boundary del omega, the field variable must be equal to the prescribed function g of x and y. Let's, for simplicity, assume that our domain is a square-shaped domain of size 1 by 1. Again, our domain is marked as omega. The boundary of our domain, the thick white line, is del omega. And we do a discretization, a spatial discretization of this domain of x and y along x and y points, coordinates. Let's assume that we use n sub x, generate n sub x points along x and n sub y points along y, and obtain this grid that we see. And each of those coordinates are marked as xi, y, x sub I, y sub j, etc., and they're the addresses of our grid points. If we choose our spacing to be h sub x and h sub y along the x and y directions respectively, then we can easily determine the addresses of points xi, yj using simple algebra. So if we have our points ranging from x sub 1 through to x sub nx plus 1 along the x direction, and likewise y sub 1, y sub 2 through to y sub n sub y plus 1 along the y directions, then the algebraic relationships I mentioned a second ago are as follows. X sub I, the address of the ith point, ith grid mark along the x direction, is merely I minus 1 times hx, the spacing along x. And the similar expression is valid for also y. So now we have discretized our domain. Each of these points can be determined with the knowledge of how many points are being used and what the spacing among the points are. Then the next goal is to determine an approximation or approximations to the second derivatives of the field variable at a given point, such as x sub I and y sub j. Why am I interested in obtaining approximations to the second derivatives? Well, because the Poisson equation or the Laplace equation contains those derivatives, and I'd like to discretize those derivatives and write them in algebraic form rather than in differential form. And I am marking 4 points around a given interior point, like x sub I, y sub j, and with those 4 points, with the values of the field variable at those 4 points and the value of the field variable at the center point, I'm going to try and come up with approximations to the derivative of u, second derivative of u with respect to x and y. So using the formulas we have derived earlier on numerical approximations to derivatives, I can write the approximation to the second partial derivative of u with respect to x using a central difference formula. So I sample my field variable to the right of the blue point, meaning u at x sub I plus 1 comma y sub j, and to the right of the blue point, meaning u of x sub I minus 1 comma y sub j, and then add them up and subtract from them 2 times u at the center point, divide the result by square of the spacing. That's a second order central difference approximation to the second derivative. I can repeat this procedure for the partial derivative with respect to y, and they have now been completely discretized. So here they are again. Using the yellow points and the blue point, I approximated the second derivative with respect to x, and using the red points and the blue point, I have approximated the second derivative of u with respect to y. For simplicity, I'm going to just use subscripts to denote, for example, u evaluated at x sub I and y sub j, and call that simply u sub ij. Likewise, I need to evaluate my right-hand side of the governing equation at these grid points, the driving function f. So I'm going to call f evaluated at x sub I and y sub j simply as f sub ij. If I substitute these results for the second derivatives of u into the governing equation using the indices, using the index notation, I will get the following equation. The first term is the second derivative of u with respect to x. The second term on the left-hand side of this equation is the second derivative with respect to y. And then the right-hand side is the discrete sample value of the driving function, f sub ij. And this equation is supposed to be valid at all the interior points in the domain. So I am going to have as many of these equations as I have interior points. And hopefully I'm going to have the same number of unknowns in this problem so that I can find a unique solution to this problem. As you can see, if I look at any of the interior points, if one of the interior points I'm looking at has a neighbor that happens to be on the boundary of our domain, I would need field variable values from those points. And where do I get them from? Well, I get them from the equation in the yellow box, because they are prescribed through the function g of x and y. This means that I am indeed going to have as many equations as unknowns. So the boundary data will come from there. and then for all the interior points I have to satisfy the equation in the big blue box here. And then if I have a point, a light blue point that has a neighbor that happens to be on the boundary, the value of the field variable there is not unknown, it is known, it is prescribed. I'm going to be able to get that value from the big yellow box. So let's go about solving some examples. We can further simplify our notation by assuming that our spacing along the x and y directions are uniform and we have the same number of points for our squared domain. So wherever I see an h sub x or y, I put h. Likewise, n's are replaced with n sub x and y are replaced with n. And the governing equation I had before can be written as follows. Again, I have as many of these equations as I have interior points, and I will only have as many unknowns. So this is a perfectly well defined problem. As it turns out, it is not singular with the coefficients that we have, and we can definitely use the Gaussian elimination to directly solve for the unknown field variable at all the interior points. So once we solve those equations, we're going to end up with u sub ij at every interior point, and the problem will be solved. There happens to be an alternative solution method to this, which avoids the direct Gaussian elimination, because if our grid is very highly refined and we have thousands, hundreds of thousands of unknowns, then to solve that matrix equation will be a big trouble, and an iterative technique might actually be preferable. So what is the iterative technique about? Well, it is almost like a fixed point iteration, or some people refer to it as a relaxation scheme, in which we write the equation in the blue box in a slightly different format and state that u sub ij is equal to the average of all the neighboring points to its left, to its right, above it, and below it. And so we subtract the h squared over 4 times f sub ij from that. This is indeed the same thing as the governing equation. But what we do is we go to every interior point and do this averaging. We find the values of the current values of the field variables of its neighbors, we average them, meaning add them up and divide it by 4. And we subtract the driving force term if it exists, if it has a value at that interior point. And then we just keep repeating this procedure and go through all the interior points one by one. And come back to the original point that we started with, and see when we repeat this procedure, the value of the field variable changes there. If it does change, then we keep sweeping. If it doesn't change, that means it has stabilized and converged, and that we have found the solution. So we would repeat this thing until convergence. I'm going to show you a MATLAB implementation of the iterative scheme, not the Gaussian scheme, which we talked about earlier, so that you can see how it works clearly. Also, before we get there, we need to talk about the accuracy of the method. If you do an error analysis using the central difference approximations that we adopted, you'll find that the difference between the analytical solution and its numerical approximation is going to be of the order hx squared and hy squared, which means if we refine our mesh, meaning if we double, for example, the number of points along x or y directions, our error is going to reduce by a factor of 4. So that's the error behavior, refinement behavior of our scheme, which is based on a central difference approximation. So here's the MATLAB implementation of the iterative scheme. This is implemented as a function, and it actually solves the problem on a square domain we've talked about earlier. So here's the function defined at the top, Poisson, and there's some input f, g, n, tall, maximum iterations, and the result is u. So what are the input meanings of those input variables? Well, f denotes the right-hand side function, that's our driving function. G denotes the Dirichlet boundary value function. So those are supplied to us by the user who calls this subroutine. Those are indeed function handles. N is the number of subintervals along x and y directions that the user wants to use. Tolerance is the relative error tolerance of the iterative solution scheme, and there's a default value prescribed for that, 10 to the minus 5, and the maximum number of iterations allowed is 10,000, and the user can, or rather the default value set by us is 10,000, and the user can specify something larger or smaller if the user wants to do so. And then the subroutine, this MATLAB function will calculate the solution at all the points, including the interior points and the boundary points. Fill it up, fill an array, u sub ij with the correct values, and send it back outside. So here's that first check where we are checking whether the user supplied indeed the tolerance value and the maximum number of iterations. If the user didn't supply those, default values are adopted. Then the discretization takes place. Given the number of subintervals, we calculate the h, the separation between grid points along x and y directions. And then we also fill in our driving function, the right-hand side function, f sub r, by using the user-supplied function, lowercase f. So we call that function with f-eval. We evaluate it at all the interior points, and we fill the results into f sub r for later use. Then the first order of business after that is to fill in the values of the field variable capital U at the boundaries. So 4 statements take care of the 4 edges of our squared domain, where g is evaluated, the g being the function handle supplied by the user, which gives us the prescribed values of u at those locations. Then then a while loop is constructed, and this loop, as you can see, will continue on until the relative error is less than the tolerance and the maximum number of iterations is less than the maximum number of iterations. If one of those conditions is violated, it's going to stop, meaning you will have either converged by getting the relative error less than the tolerance value, or you will have exhausted the maximum number of iterations and therefore you have to stop. Okay, so later then 2 variables are set, error is equal to 0 and umax is set equal to 0, and then inner loop is constructed. It's a double loop which loops over all the interior points marked by I equals from 2 to n and j equals from 2 to n. The first thing that's done after that inside for each of those grid points, interior grid points, is a temporary value is calculated, which is indeed equal to that average we talked about. 1/4 of the sum of the field variables in the neighboring points. Subtract from that this fr, which is the driving function multiplied by h squared over 4, right? So we take that temp value and we actually subtract the current value of the field variable at the interior point from this temp value. Of course, in the very beginning, the interior point values are all zeros. That's what we have initialized it in the green box, if you recall. So there's going to be a difference, and the absolute value of this difference is recorded. And then we record it to the maximum difference we have ever recorded up to that point. And if the maximum error that we have recorded up to that point was smaller than the difference we've now calculated, we set the maximum error to this value that we've just calculated. You'll see later why we're doing this. But after we've done that, then we can assign the temporary value that we have calculated as the new value of the interior point. And then we also store that absolute value of that temporary value and then compare it with the umax that we have ever recorded. So we use the temp or umax as a storage value to record the maximum field variable value in all the interior points in all the iterations. So as we come out of these inner loop and the while loop, we will have ended up with the maximum value of u for calculating basically the relative error. And then at the end of these iterations, when we come out of the loops over I and j, we will have come out with not only updated values of uij, all the interior points, but also with the maximum error that we have ever recorded. So these iterations end like that, and let's see how it works. Here's an example problem where we have a driving function that's equal to negative 2 pi squared times sine pi x sine pi y. Our domain is square shaped. The ranges of our domain are from 0 to 1 in both directions. And a Dirichlet boundary condition is prescribed, and this one is extremely simple, that the g of x and y is 0 everywhere along the boundary. So we're just merely setting the u values at equal to 0 at those boundaries. And because the driving function is fairly simple, there exists an analytical solution for this problem. And this indeed is the analytical solution. What you can do is you can plug it into the governing equation to check to see if it actually satisfies it. And then you can also plot it. So it looks like that in the figure. The three-dimensional plot, the surface plot, shows the value of the field variable at all points in the interior and on the boundary. And not surprisingly, as expected or as prescribed, the values of the field variable on the boundary are zeros. And for this problem, it attains a maximum value at the center of the domain, as it turns out. It looks like a little bubble. So let's try and solve this problem with our MATLAB function. If we feed the Dirichlet boundary condition and the driving function to the problem and obtain solutions, we end up with an approximation to the analytical value. And as you can see, the plot on the left is a plot of a numerical solution, which is determined for separation h equals to 0.0625. So for that discretization, this is the solution we get. Of course, the solution is not without errors, and the errors are plotted on the right-hand side, which looks like an inverted bubble. Of course, on the boundary of the domain, there's no error, because those values are not calculated, they're prescribed. So the numerical solution matches the analytical solution exactly at the boundary, as it should. But everywhere else, there's a little bit of an error. And this plot may suggest that the error is large, but in fact, this error is very small. Look at the multiplier of the y-axis, the error axis, it's 10 to the minus 3. So this is indeed a very, very small error compared to the solution we have. The solution has a peak value of almost 1, and this maximum error that we record is almost 2 times 10 to the minus 3, which is a very small number compared to the actual solution. So this is a good approximation. We can repeat the solution with different h values by increasing the refinement along x and y directions uniformly. If we use 4 grid points, we get maximum error of 5.3 times 10 to the minus 2. If we double the size, double the number of points along the x direction, compute the error, take the ratio of this maximum error to the maximum error from n equals 4. The ratio is almost 4. And if we keep repeating this procedure, we'll see that, as expected, the error is reducing by a factor of 4 as every time we double the number of points along x and y directions. In this case, uniformly.